These are going to be our notes on optimization. So first let's talk about what is optimization. Optimization are going to be applications that ask you to make some kind of physical situation the best that it can possibly be. And that's going to look like a lot of different things. I mean, it can be things like, hey, can you make this the fastest it can possibly be? Can you make it the cheapest? Can you make it cost the least? Can you make something able to bear the largest amount of weight possible, a best fit, or hold the most? I mean, so optimization is kind of a broad heading for all of these ideas, but they all have one thing in common. They all involve either a maximum or a minimum. I mean, if you're looking at the fastest, then you're looking at minimizing time. Cheapest, you're looking to minimize cost. If you want something to hold the most, it needs to maximize the weight it can bear. So they all involve maxes or minimums in some kind of fashion. When we want to solve optimization problems, we have some guidelines. Now, these are not hard and fast rules, nor do they necessarily occur in the order in which I'm presenting them to you, but these all pretty much need to be addressed as you're going through an optimization problem. So of course, first, as usual for any application, you read the problem carefully, you identify your variables. What do you know? What are you looking for? And if it's appropriate, you draw a figure with your quantities labeled relevant to that particular problem. We will need to find a formula for whatever it is you're trying to optimize, whatever it is you're trying to make the best. Sometimes that's called an objective function. You need to identify what are usually deemed your constraints. And what we mean by that are conditions specific to the problem that you're looking at. Just kind of a quick example. For example, if you're talking about a box, the volume of every box is length times width times height. Okay, that's true for all boxes. But let's say, for example, your box happens to be a cube. And what that means is all dimensions should be the same. Well, in that case, you wouldn't identify volume as length times width times height. You'd identify it as side cubed, because all the sides would be the same. So it'd be side times side times side. So these are going to be conditions specific to your problem. We use those constraints to eventually get that objective function as a single variable function. We want it as a function defined by only one variable. And once you have it as a function of one variable, you're going to be able to identify the possible values of that variable. In other words, you're going to examine the domain, but the domain won't just be based on the function, it will also be based on the physical restrictions of the problem. So again, just a quick example. Let's say your objective function is a function of time. Well, time definitely can't be negative, for example. So you would automatically say time had to be greater than 0. So that's what we mean by physical restrictions of your problem. And then because we have that objective function as a function of one variable, we're going to be able to take its derivative and use methods of calculus to find the absolute maximum or minimum. Now these are absolute maxes and mins, which means not only are we going to be looking for critical numbers, we're also going to have to do things like perhaps consider endpoints of our domain, since these are absolute maxes and mins, or consider what happens as you let your variable get infinitely small or infinitely large. Each problem is going to have a little bit of a different approach, so we'll take a look at them as we go through, but we will be taking all that into consideration. So those are some general guidelines. Let's look at some specific examples. So this is what is affectionately known as a farmer and a fence problem. Generally, farmer and a fence problems are pretty much what they sound like. You've got a farmer, he's trying to enclose some kind of space, and your job is to optimize something about that space. So in this particular problem, you have a farmer with 400 feet of fence for constructing a rectangular corral. One side of the corral will be formed by a barn and requires no fence. 3 exterior fences and 2 interior fences partition the corral into 3 rectangular regions as shown. So here's the as shown. What are the dimensions of the corral that maximize the enclosed area? And what is the area of that corral? So here's our barn. We have our fence. I went ahead and labeled these for you just so that we're all on the same page as far as which dimensions are represented by which variables. So let's talk about what it is that we want to optimize. Okay, we're going to optimize something, maximize or minimize it. In this particular problem, what we're looking for is what are the dimensions of the corral. So we are looking for dimensions, but we're looking to maximize the enclosed area. We want to optimize area. So we want to max area. Okay, so as an objective equation, what we need to do is write an equation that's going to optimize that. Okay, this is a rectangle, and in general, the area of any rectangle is going to be its length times its width. So in this case, that is going to be x times y. The fact that you have other partitions in here does not change the area of the corral as a whole. So A equals x, y. That's what we're going to be working with for our optimization. Now our constraint for this particular problem, the constraint is going to be a few things. I mean, first of all, we of course are going to have to deal with this particular diagram. Our shape is set for us. We are constrained by the shape that we're looking at, but also by the amount of fencing that we have. We only have 400 feet of fence. Okay. Now, what the amount of fence is going to represent is essentially all of these, the lengths of each one of these lines. It's a linear measurement. In other words, it's kind of a perimeter idea. Now, it's not perimeter of the rectangle in the traditional sense. The perimeter of a rectangle would just be the distance along the outside of the rectangle. We also need to account for these two extra partitions that are going to come into play. So our particular perimeter equation is going to be, you have 1y, because you don't need any fence along the barn, so you're going to have 1y, and you're going to have 1, 2, 3, 4 x's. And when you're done adding all that together, you're going to get 400 feet. So that's our optimization equation and our constraint equation that we're going to use. Okay, so since the area is our optimization equation, what we're going to want to do is eventually be able to take the derivative of this area as a function of something. The problem is right now, area is a function of both x and y, meaning there's x's and y's on the right side of this equation. We need to eliminate one of them before we can take the derivative. So here's where our constraint equation comes in. Now technically, I can solve this for either variable, either x or y, and substitute it into the area equation. So since I'm actually going to get a choice, I'm going to choose to solve this for y. It eliminates the fractions. So y is the same thing as 400 minus 4x. That's my replacement. So area can be rewritten as x times 400 minus 4x. And notice that area is now a function of x. It's a function of only one variable, which means I'm going to be able to take its derivative. Now that it's a function of one variable, we can talk about things like domain. So it is a quadratic function. Therefore, technically the domain of it would be all real numbers. But again, you got to worry about physical restrictions for this. So x represents the length of one of those dimensions of the fence. So therefore, it can't possibly be negative. So 0 definitely is less than x, also known as x is greater than 0. The largest that x can possibly be, again, in theory, it should be able to go to infinity, but if you look back at the diagram, if we used all of our fence to take up x, meaning all 400 feet went to these x dimensions, that would make y equal to 0. Each one of those x's could only be 100 feet long. So the largest that x can possibly be is 100. So that's how we determine the domain of this particular function. So we know we need to optimize this. We need to find its absolute maximum. So we need to go through some of the techniques that we learned earlier in this course. Things like finding critical numbers. And critical numbers are, of course, determined by the derivative. So the derivative of this with respect to x is going to be 400 minus 8x. And to find the critical numbers, you worry about where your derivative doesn't exist and where it's equal to 0. It exists everywhere, and it's going to be equal to 0 when 8x equals 400, also known as x equals 50. And if x equals 50, we know from this equation over here that y will be 400 minus 4 times 50, also known as 200. And those are both measured in feet. So now before we walk away from the problem and say, oh, those must be the dimensions that maximize my area, we need to check our endpoints. Remember, for absolute maxes and mins, the steps are to find your critical numbers and then evaluate the function at your critical numbers, so that's a of 50, but also you need to check your endpoints, so that's a of 0 and a of 100, based on the domain that we already established. So if a is 50, and this is part of our question anyway, we need to find the area, then the area should be, you can either plug in here and just plug in 50 for x, or since I already found y, I can plug into a equals x times y. Either one will get you the same answer. I'll just plug into x times y. So that's 50 times 200, also known as 10,000, and that's going to be square feet because it's an area measurement. If x is 0, then your area is 0. And if x is 100, that will make y 0, which is going to make your area 0. So definitely the dimensions that are going to get you the largest area are going to be x equals 50 feet, y equals 200 feet, and the area that you're going to get, the largest possible area for this is going to be 10,000 square feet. And that's our farmer and the fence problem. Let's take a look at another one. This kind of problem is referred to as an inscribed shapes problem. It's usually one shape put inside of another. That's what we mean by inscribed. So it can be any two shapes. This particular problem, we're looking for the radius and the height of a right cylinder of largest volume that can be inscribed in a right circular cone with radius 6 inches and height 10 inches. So here's just kind of what that looks like. So your cylinder is inscribed inside your right circular cone. Okay, so let's talk about our objective here. Our objective, what is it we're looking to optimize? We want to find the radius and height of our right cylinder, but that right cylinder has to have the largest volume. Okay, those are the kind of words you're looking for to know what to optimize in these. So largest means we're looking for a max. So we're looking to maximize the volume, but specifically of the cylinder. Okay, so in general, we would want to know then, well, what kind of equation represents the volume of a cylinder. So the volume of a cylinder is given by pi r squared h in general. Now I'm going to be a little hesitant here though to use those letters, because if you look at my diagram, you see how I already have an r and an h going on? Those are the radius and the height of the cone, not of the cylinder. And the radius and the height of the cone are not going to be the same as the radius and height of the cylinder. So just for purposes of this particular problem, I'm going to not use r's and h's. I'm going to use x squared y, okay, with the understanding that I'm letting x be the radius and I'm going to let y be the height. That way I don't get confused over what r represents and what h represents. So if you notice, my volume is not a function of one variable. Again, it's got both x's and y's over here. Eventually, my goal is to find the critical numbers of this objective equation and by taking its derivative. But I need to get rid of one of those variables before I can do it. So here's where our constraints are going to come in. Okay? Our constraint has to do with literally what is physically constraining it. The cone on the outside is physically constraining this cylinder. Okay, we know that we have a cone. It's got a radius of 6 and a height of 10. Now those are given and those are constant. So we know that this distance here is 10 and this distance here is 6. Okay, those are given to us. So we need to somehow be able to use that to talk about the radius and the height of the cone. And I've kind of started to draw it here, but this particular one, see how there's a hypotenuse here? We're looking at a right triangle, but in addition to that, what you've got are two triangles within each other. These are similar triangles. So let me draw those by themselves out here so it's not too confusing. So what we have are two similar triangles where this distance is 10. This distance is 6. This is my radius of my cylinder, so that's going to be my x. Now the height of my cone technically goes right here. And if you know kind of where I'm aiming with similar triangles, you want to get some ratios that are similar between similar triangles. So the large red triangle is going to be similar to the smaller blue triangle. That's supposed to be a triangle. So let's see what kind of ratios we can set up with that. The two legs of my big triangle are 10 and 6. So if I take the ratio of the legs of the large triangle to the legs of the blue triangle. Now, this one is obvious, that's x. But this one, be a little careful. This is the other leg, and it's not y. It's actually what's left over after you take y out of 10. So it's 10 minus y. So there's a ratio, there's a constraint equation that contains the same two variables that are present in my objective equation. So technically I can solve for either x or y in the constraint and use that to substitute into my objective equation. So when I look at this objective equation though, I'm probably going to prefer to substitute in for y. It's not that it would be wrong to substitute in for x, but if I do, I'm going to have to square the result, and I want to try to avoid that if I can. It's not that it's wrong, it's just more work. So I'm actually going to solve my constraint for y. So we'll get 10x equals 60 minus 6y, which says that y is equal to 10 minus 5/3 x. That's my y. So I'm going to use that and substitute into the objective equation. Here it is. And now notice it is a function of only one variable. This is now v as a function of x, which means I'm going to be able to do things like talk about its domain and take its derivative. Let me go ahead and distribute this. That'll make my derivative a little bit easier to take. So we get 10 pi x squared minus 5 pi over 3 x cubed. So again, as far as domain goes, at first glance, the domain of this should be all real numbers because it's a cubic function. But since x represents the radius of my cylinder, the smallest it could possibly be is 0. It can't go negative. And then if you look back at the diagram, the largest it can possibly be, this is my x, the largest it can possibly be is the same as the radius of that cone. It can't go outside the cone. So the largest it's going to be able to be is 6. Okay, we're ready to take its derivative. So the derivative with respect to x is going to be 20 pi x minus 5 pi x squared. And we're going to find the critical numbers for this. So we are going to set it equal to 0. So I'm going to factor out a 5 pi x from each one of these. And what I'll get is 4 minus x equals 0, which has two solutions, x equals 0 or x equals 4. X can't really be 0 because then you wouldn't have a cylinder, so we're going to call that out of domain. So x equals 4 is my critical number. I then need to examine the volume at 4. But I need to compare that to the volume at the endpoints. Now these, again, these are going to be pretty simple for this one, v of 0 and v of 6. But I want to do this in kind of a work smart, not hard kind of way. If you take a look, if you plug 0 into this volume function, this factor will be 0, which will give you a volume of 0 overall. And if you plug in 6, this factor will be 0, because you'll have 10 minus 10 in here. So that volume will also be 0. But if you want to just check real quick to make sure that that's actually going to be a maximum, if you look at 0 to 6 with 4 as a critical number, look at your derivative. It's here in its factored form. If you plug in a number like 2, what you're going to get is a positive number from this factor and a positive number from this factor, so positive overall. If you plug in something in between 4 and 6, like 5, you're going to get a positive number for this factor, but a negative number for this factor, which means that your volume function will go from increasing to decreasing. In other words, that's a maximum. So as far as verifying that this is the absolute maximum goes, we're in good shape. So our radius, which is our x, is going to be 4 And in this problem, that's measured in inches. And our height, that was our y value. Our height was given by our y, which was 10 minus 5/3 times x. So that's 10 minus 5/3 times 4, also known as 10/3, 3 1/3 inches. And we want to go ahead and leave that exact. Don't change that to 3.3 or anything like that. And there's our answer for this one. Before we take a look at the next problem, I want to talk about a conceptual idea that's going to help us as we go through it. I want to talk about the difference between optimizing f of x equals the square root of g of x versus optimizing f of x equals that same function without the square root. Okay, so when we go to optimize these, optimization means we're going to end up looking at critical numbers, which means we need to take a derivative. So take a look at the derivative if you have the square root. Your derivative in this case, the square root is just an exponent of 1/2, so it will be 1/2 times, you hold the inside function, this is chain rule, raised to the new power of negative 1/2. But then you multiply times the derivative of the inside function, times g prime of x. So if we look for critical numbers, we need to take a look at where the derivative doesn't exist and where it's equal to 0. So I'm going to rewrite this just a little bit. Anything with the negative exponent goes down to the denominator, and then the 2 is down in the denominator. So we'll have 2 times the square root of g of x times g prime of, with a g prime of x in the numerator. And when we go to set this equal to 0 to find critical numbers, so notice this is now a fraction, and we're going to be setting it equal to 0. So when is a fraction equal to 0? Well, when its numerator is equal to 0. So this will be equal to 0 anytime that g prime of x equals 0. So this is what we would end up doing to optimize the function if it started with a square root. If the function didn't have a square root, all you would do to optimize this is literally just take g prime of x and set it equal to 0. Notice in both cases, you're taking the derivative of what's either under the square root or the function without the square root and setting them equal to 0, which is why the conclusion that we end up drawing is that instead of optimizing the square root of a particular function, you can instead optimize the function under the radical by itself. This does not imply that the derivatives are the same. The derivatives are not the same. But once you work with the optimization and finding the critical numbers, the process ends up being the same. So that's going to help us out quite a bit in the next example. Let's take a look. We want to find the points on the graph of y equals 4 minus x squared that are closest to the point 0, 2. Okay, so this is another type of problem where you're given a graph and you're trying to find points on that graph close to a given point. So let's start off the same way we've started off the other ones. We want to talk about our objective and what is it we're trying to optimize. Okay, so we're looking for closest. Okay, when we talk about how close two things are to one another, we're talking about the distance between them. And if we want that distance to be close, we're looking to minimize that particular distance. So that's our objective, minimize distance. Well, if that's what we want to minimize, we're going to need an equation to describe distance. Here comes the distance formula. And this is a formula that we do assume you have memorized. Distance formula in general is x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared, all under a big square root. Okay. Of course, you cannot split this square root across the addition. You can't take the square root of the first term and the square root of the second term in order to simplify it down. Now, our particular distance is going to go between 2 points. This is the general formula for the distance between x sub 1, y sub 1, and x sub 2, y sub 2. Our distance specifically goes between 0, 2, and then some point on this graph. And that point is what we're looking for. So we have no idea what it is. So we'll go ahead and call it xy. So our distance specific to our problem, and that's why this is our constraint. I didn't write down the word constraint, but this is our constraint. The given point is 0, 2, and the other point must be on the graph of y equals 4 minus x squared. So our distance is going to be the difference in the x values. So x minus 0 squared plus the difference in the y values, which is y minus 2 squared. So if I clean that up just a little bit, we get the square root of x squared plus y minus 2 squared. Again, please do not square root those individually. You can't do it across addition. So notice at the moment, I've got a good objective equation except for the fact that it's not a function of one variable. I have x's and y's on the right-hand side. I need one of them to go. So remember, the constraint was you were given a specific point and we're looking for another point, but that point must be on that graph of y equals 4 minus x squared. So this is our other constraint. Believe it or not, this is actually kind of nice. They pretty much handed you your substitution for one of the variables in this process. So our specific objective equation is going to be d equals the square root of x squared plus, and in place of y, I'm going to put in 4 minus x squared. We still have minus 2, and it's still squared. So our function, specifically as a function of x, is the square root of x squared plus 2 minus x squared squared. You can FOIL this out, but I'm going to choose to leave it as it is. Now that we have it as a function of one variable, we can look at its critical numbers, which means we're going to take the derivative of this. But this is where that little conceptual conversation that we just had comes into play. I can take the derivative of this involving the square root, but because I'm planning on not just taking the derivative but optimizing, I can instead just optimize what's under the radical, which will make my derivative a lot easier to take. To indicate that I'm just dropping off the square root, I'm not squaring both sides. What I'm going to do is I'm going to switch this notation and start calling this a capital D instead. We'll call it capital D and say that that's equal to just the x squared plus 2 minus x squared squared. And we're going to optimize this instead, okay? So in order to do that, we're going to take its derivative. We get 2x plus, don't forget chain rule on this one, so that's 2 times 2 minus x squared to the new power of 1 times the derivative of the inside function, which is negative 2x. And this can simplify to, let's see, we'll get 2x, let's see, that's minus 8x, and then this will change to a plus 4x cubed, which says, when you simplify, we get 4x cubed minus 6x. So we're going to want to set this equal to 0. We factor out what's common to both terms. We take out 2x, and we're left with 2x squared minus 3 equals 0, which says our critical numbers. We get x equals 0 from the first factor, and x equals plus and minus the square root of 3 halves for our other critical numbers. Okay, so we need to plug our critical numbers into our distance function, and please keep in mind we're back to using the one with the square root. Okay, we got rid of the square root for purposes of optimization, but if we actually want to plug this in, we have to go back to the one with the square root. So we need to find d of 0, d of the square root of 3 halves, and technically you should also do negative, but what I'm noticing when I'm looking at this function is when you input any x value, it's going to get squared, so whether you put in the plus or the minus, you should end up with the same result. So I'm not going to do the calculation twice. We should also take into consideration, in theory, kind of the endpoints of this, but this one, if you take a look at that distance function, its domain is actually going to end up being all real numbers, because what's under the square root is going to come out positive regardless, because both terms are squared, so we don't have to worry about negatives under a radical. And then you can put anything into each one of these polynomial type terms. So technically, x can go to negative infinity or positive infinity. So if x happens to go to infinity, or negative infinity for that matter, because again, when you square it, the negative will go. What's going to happen is this term's going to go to infinity, this term's going to infinity. You are adding them together. So overall, d is also going to go to infinity. So remember, we're trying to minimize distance, not maximize it. So any other value of x outside of these critical numbers should give us a larger distance. So that's the logic behind the fact that we only need to consider these particular critical numbers, and we'll know that those are absolute minimums once we actually identify which is which. So when you put 0 into your distance function, This term goes to 0. Here we're going to get 2 squared, also known as 4, but you're going to take its square root, so you're going to get 2. When you put in plus or minus the square root of 3 halves, pardon me, I wrote that wrong. That's the square root of 3 halves. The whole thing's under the square root. What you're going to get is the square root of 3 halves plus 2 minus 3 halves squared. And then the decimal approximation for that's going to be 1.323, give or take. 323, that's a 3. So clearly, if you're looking to minimize distance, 0 isn't doing it. 0 is actually much farther away from the point 0, 2 than if you were to just use x equals plus and minus the square root of 3 halves. But now the question did ask us to identify the points. So y was equal to 4 minus x squared, so that's the square root of 3 halves squared. And again, when you square it, it won't matter whether it's plus or minus. So you'll get 4 minus 3 halves, which is 2.5, so 5 halves. So your two ordered pairs are the square root of 3 halves, 5 halves, and the negative square root of 3 halves, 5 halves. Those are the 2 points on the graph closest to the point 0, 2. Let's take a look at another example. So in this example, we're looking to minimize cost, and we're actually going to do 2 different examples of this type of optimization problem. In this one, what we're looking to do is deal with a cylindrical can made to hold 1 liter of oil, and we want to find the dimensions that will minimize the cost of the metal to manufacture the can. So to begin with, what we're looking to optimize in this case is the cost to manufacture the can. So we're looking to minimize cost. Okay? So of course that means we're going to need an equation that describes the cost of manufacturing this can. Now the trick with this one is there's no mention of any dollar amounts. They haven't said, hey, the material costs blank amount. Well, that's because if what you're manufacturing has consistent material throughout, meaning it's the same material no matter which part of it you're manufacturing, the cost just boils down to use as little material as possible. Now in this case, because we're manufacturing a can, what we're actually looking to do is to minimize the surface area of the can. In this case, it's in the shape of a cylinder. Now that's not going to be true for all cost optimization problems. If, for example, they had said, hey, the sides are going to cost blank, a certain dollar amount, and the bottom and top are going to cost something else, well, then it matters how much of that material you were going to use. So for us, though, all we have to do is minimize surface area in this particular case. So the surface area of a cylinder is given by 2 pi RH, that's the surface area of the side, plus, if it's got a top and a bottom, that will be 2 pi r squared. Pi r squared represents the area of the circle, and then there's 1 circle for the top and 1 circle for the bottom. So this is the surface area of our cylinder. Our constraint in this case is the fact that it has to hold 1 liter of oil. Now, when we see measurements like liters, you need to think about what that represents as far as measurements, and in this case, that's volume. Now, the only hiccup that we can run into with this is the following. Eventually, we are looking for dimensions of a can. So things like, what are its radius, what are its height. Those are linear measurements, and we need to know what type of linear measurement to put on that. Is it inches? Is it centimeters? Is it miles? And as long as the only label that I'm working with is liters, that's not obvious. So what we need to do is convert this volume measurement into something that has more of a linear measurement unit on there. So 1 liter is 1,000 cubic centimeters. You can tell it's also a volume measurement because of the fact that it's centimeters cubed. And anything with a cubic measurement is going to measure volume. So the volume of a sphere in general is going to be pi r squared h. And so for us, that needs to be equal to 1,000 cubic centimeters. So notice that our optimization equation has too many variables again. S is not a function of just H or just R. So we have a constraint equation that also contains R's and H's. What we need to do is solve for one of the variables and substitute into the optimization equation. I'm going to solve for H because it does not contain a square, and therefore I do not have to worry about square roots. So H is equal to 1,000 over pi r squared. So when we substitute that in to our optimization equation, what we're going to get is that S is equal to 2 pi r. In place of H, we put in 1,000 divided by pi r squared plus 2 pi r squared. And now notice that our surface area is just a function of r. And let me clean that up a little bit as we move to the next slide. So our surface area function as a function of r, as a function of the radius, is going to be 2,000 divided by r plus 2 pi r squared. Now, the domain restrictions on this. This is a physical representation of a radius, so it absolutely can't be negative. Now, in theory, we're building a cans, but in theory, we can make this radius as big as we like. I mean, you can make it very, very large. So we'll keep that in mind when we try to come up with our final answer, but basically this can run anywhere between 0 and infinity. So to come up with our critical numbers, we need to go ahead and take the derivative of s at r. That's going to be negative 2,000 over r squared. You can either use quotient rule to get that, or you can just bring this up as 2,000 times r to the negative 1 and use power rule. Either one works. Plus 4 pi r. Find our critical numbers. We set this equal to 0, in which case we have that 2,000 over r squared has to be equal to 4 pi r. Little cross multiplication says that 4 pi r cubed equals 2,000, so that r equals the cube root of 500 over pi. So that's our critical number for our radius, but we also need to take into consideration the fact that it could be 0 or it could be infinity. But notice, if r approaches 0, and technically it would have to approach 0 from the right because it can't be negative, what's going to happen is the fraction is going to have a denominator that's getting infinitely small, which means that the fraction overall is going to get infinitely large. And so you'd have something infinitely large plus this term would go to 0, but still that would tell us that the surface area would approach infinity, which is not what we want. We want to minimize this. If r approaches infinity, so we'll check the other end point, if you will. It's not really a point, but end point. Then while the first term, the fraction, will go to 0 because its denominator is getting infinitely large, the second term will go to infinity. So also s will go to infinity. So neither one of those is going to work as far as minimizing our cost. So this is in fact going to provide us with our absolute minimum. We just need to answer the rest of the question and find h. So h ends up being, remember it was 1,000 divided by pi r squared. When we solved for h, that's what we got. So for us, that's going to be 1,000 divided by pi times, that'll be 500 over pi. It was to the 1/3 in the radius, but we're going to square it, so it's going to go to the 2/3. Which with a little manipulation, you can show that this becomes 2 times 500 over pi raised to the 1/3, which if you notice, that is the cube root of 500 over pi, also known as r. So the height should be twice the radius. And those are the dimensions that will minimize the cost in this particular example. Now let's look at another example where we're asked to minimize cost. But in this one, we'll be given different dollar amounts for different parts of what we're manufacturing. Okay? So for example, a rectangular storage container with an open top is to have a volume of 10 cubic meters. Now notice, unlike the last one, this one already has a cubed linear measurement on it, so I don't have to convert this one. I can just leave it as 10 meters cubed. The length of its base is twice the width. Material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. Find the cost of materials for the cheapest such container. So we are still looking to minimize cost. So for this one though, we actually do need to take into consideration the fact that different parts of this cost different dollar amounts. So let me draw a rectangle here. We also have a ton of other constraints. Essentially, everything in this part of the problem represents some kind of constraint. It gives us the shape of our container, it gives us some of the dimensions of our container, along with the dollar amounts for different sides. So we need to take all of it into consideration. So we know that the volume is 10 cubic meters. Now, in general, the volume of a box is length times width times height. However, notice this sentence. The length of its base is twice the width. So now the base of your rectangle is the part that sits on the bottom. The length of its base is twice the width. So if we call this dimension the length and this dimension the width, call that one the width, the length is twice that width. What that's going to do is eliminate one of our variables. We don't have to have an L in this. We'll have W, 2W. Now what it didn't tell us anything about is the height, so we will still have an H in here. So this particular storage container, its volume isn't really going to be length times width times height. It's going to be 2W times W times H. In other words, 2W squared H. Now that is a constraint equation. That will help me start to eliminate some of my variables once I start working on my cost equation. So what we now need is an equation to describe the cost of this. So let's start with the base. We know how to find the surface area of the base. The area is just going to be 2W, that's one of its dimensions, times W, that's its other dimension. Its cost is going to be that many square meters, 2W times W, times how much it costs to produce each one. Well, because it's the base, that's times 10. This is the cost of the entire base. Okay, so now we need to do the same thing for the sides. The problem with the sides is they're not all the same. I mean, this front panel is 2W by H, whereas the side panel is W by H. So we're going to have to consider the front and the back separate from the two sides. So let's do front and back first. The front and back, their surface area is 2W by H. Now there are two of those panels, so we're going to multiply by 2, one for the front, one for the back. And then the cost for that is $6 per square meter. So that's going to give me the cost of the front and the back. And then for the sides, the surface area is WH. There are two of those as well, one on the left and one on the right. And then times its cost, which is also 6. This is the cost of all sides. Okay, so that's how we're going to create the cost equation that we want to minimize when we know that different parts of this cost different dollar amounts. When we clean this up, we end up with a cost of 20W squared. Let's see, that's plus 12WH and 24WH. So that's plus 36 times the width times the height. Now this still is not a function of one variable. I have both W's and H's in here. But if you remember from the previous slide, we had the fact that 2W squared H had to be 10 due to the volume constraint. So if we solve this, you can solve for either one. I'm solving for H because I don't have to square root anything. H should be equal to 5 divided by W squared. So when I substitute that into my cost equation, I'm going to get 20W squared plus 36W times 5 over W squared. Clean it up and we get 20W squared plus 180 over W. Now this is a function of one variable. We can take its derivative. So the derivative of the cost with respect to the width is going to be 40W minus 180 over W squared. Again, you can either do quotient rule or treat this as 180 times W to the negative 1. And because we're looking for critical numbers, we're going to set this equal to 0. That tells me that 40W has to equal 180 over W squared, so that W cubed equals 9 halves. That's a 9. So my W for this, my critical number, is the cube root of 9 halves. So as far as, I didn't really mention domain, but if you look here, again, domain of this, W can't possibly be negative because it's a physical representation. And in theory, this could go all the way up to infinity, but this is pretty much the same argument we just made for the previous example. If you let w approach the smaller quote-unquote endpoint, then as w approaches 0 from the left, the first term goes to 0, but the second term goes to infinity. So your cost would approach infinity. You don't want to do that. If you let the width approach infinity, then the first term will go to infinity, second term will go to 0. So in that case, again, cost goes to infinity. So neither one of those is appropriate if you're looking to minimize the cost. So we're going to use our critical number to do it. So the cost in that case, which is what it's asking for, it didn't ask me for dimensions, it asked me for the actual cost. What I'm going to do is plug the cube root of 9/2 into this cost function. So we get, what, 20 times 9/2 raised to the 2/3 plus 180 over 9/2 raised to the 1/3. Now this, it's a money problem. It's very appropriate to get a decimal representation and not to use an exact answer. And it's also kind of understood you should be rounding to the nearest cent because that's what we usually express cost in, dollars and cents. So if you put that into a calculator, you should get about $163.54. If we look at a wire cutting example, this one says 4 feet of wire is to be used to form a square and a circle. How much of the wire should be used for the square and how much should be used for the circle to enclose the maximum area? Okay. So we're looking to maximize area in this case. So that is what we're going to need an equation for. Now in this case though, we need to take into consideration both the area of the square and the area of a circle. So if we say, hey, our square, let's give it dimensions x all the way around, and our circle, let's give it a radius of r. They are definitely not necessarily going to be the same. So the total area, the area for the square will be x squared, the area for the circle will be pi r squared. So this is what I'm looking to optimize. Again, too many variables. There has to be some kind of constraint. And this is kind of similar to the farmer and the fence problem. We're dealing with 4 feet of total wire. That's how much distance around there is. So the distance around the square will be 4 x's, and the distance around the circle will be the circumference of the circle. So that's 2 pi r, and we know that that has to be equal to 4. So again, we can solve for either variable. It is not incorrect to solve for x, but I'm going to go ahead and solve for r. If you move everything over, we get 4 minus 4x over 2 pi. Factor out and cancel some of those 2's. We get 2 minus 2x over pi. So now when we use that to plug into our area function, we'll get a equals x squared plus pi times the radius squared. So if I factor out that 2, I'll get 2 times 1 minus x over pi. But we're going to square that whole thing. Okay, let me clean it up just a little bit. So a is now a function of x. So we'll get a of x equals x squared plus, this is a pi squared. It will cancel the pi up here, but it will still leave me with 1 pi in the denominator. Square the 2 to get 4, and 1 minus x squared. Now, of course, I can do things like square the 1 minus x and distribute the 4 after that. But I know I'm going to end up taking the derivative of this thing, and I think leaving it like this will actually make it a little bit easier to take its derivative. But before I do that, let's do the domain real quick. For the domain, we have a total of 4 feet of wire. We need restrictions on x because my area is a function of x. So the smallest that x can be is going to be, again, 0, pretty common. It's physical. It can't be negative. The largest it can be, however, it's got to make the whole square. So if we use all 4 feet on the square, the largest that x can possibly be is 1. So there we go. Now let's go ahead and take the derivative. When we take the derivative of x squared, we get 2x. Here, remember 4 over pi, that's just a constant, so it will stay out of our derivative, and then we're going to need chain rule to take the derivative of 1 minus x squared. So drop the 2, don't touch the inside function, new power of 1 times the derivative of the inside function. So when we clean it up, we're going to get I kind of want to put these two together. So technically this has a denominator of pi. So think of this as 2x times pi over pi. So I can go ahead and combine these two terms together. So I get 2 pi x. Let's see, here we'll have, this will be minus 8. I'm just doing the numerator. Minus 8 plus 8x all over pi. And we're going to set this equal to 0. So when we do that, it's the numerator we set equal to 0. Denominator is just a constant. So we factor out an x from the two terms we have, and that will leave me with 2 pi plus 8. And then we still have minus 8 equals 0, which says x equals 8 over 2 pi plus 8, also known as 4 over pi plus 4. So that's my critical number. I need to check my area at that particular value, so at a of 4 over pi plus 4, but I also need to check those endpoints, a of 0 and a of 1. Now here's where these kinds of problems are going to get a little interesting. You see, in every example we've done so far, the critical number has always been the value that gives us our optimization. In this case, it's actually not going to work out like that. If you take a look, if you have 4 over 4 plus pi and you plug it in, so you're getting things like, what, 4 over 4 plus pi squared, because I'm plugging it in for x, plus 4 times 1 minus 4 over pi plus 4 quantity squared over pi. It's a big mess, but essentially if you get a decimal approximation for this, it's about 0.56. Okay? When you plug 0 into your area function, first term zeroes out, second term becomes 4 over pi. And if you get a decimal approximation for that, that's 4 divided by 3 point something. It's bigger than 1. It's 1.27 about, give or take. And if you plug in 1, what you're going to get is 1. And then this term will zero out, so you're going to get 1 plus 0. You're going to get exactly equal to 1. So notice in this case, your critical number did not give you the largest amount of error. A of 0 did. So what we need is x equals 0. Gives the largest area. Largest area. In other words, if you look back at our diagrams and what we had designated x needing to be, x equals 0 means there is no square. So if you want to maximize the area, you need to use all of the wire to your circle. So this is an excellent illustration of why it is really important on optimization problems that you check the endpoints as well as the critical numbers. There's a chance your critical number isn't going to give you your absolute max or min, just a local one. Okay, let's look at another one. Optimizing over differing terrain. This one is especially applicable for engineering majors. Basically, the idea behind this is something along the lines of you need to get from one point to another, and there are multiple kinds of terrain in between your 2 points. And of course, some terrain is easier to cross than others. I mean, it's a lot easier to travel on, let's say, flat grassland than it is over mountains. So when you look to optimize how to get from point A to point B, you have to take the terrain into consideration. So let's take a look at this one specifically. A woman launches her boat from point A on the bank of a straight river that's 3 kilometers wide. So I'm going to start writing on this diagram as we talk. So your river is 3 kilometers wide. She wants to reach point B, which is 8 kilometers downstream on the opposite bank. So that's here. That's a total of 8 kilometers down. These are both in kilometers. Now the trick is she wants to reach it as quickly as possible. That's going to give you a hint as to what you're trying to optimize. She can row at a speed of 6 kilometers per hour, and there's supposed to be a space here, and run at a speed of 8 kilometers per hour. In other words, she can run a heck of a lot faster than she can actually row in her boat. Where should she land on the opposite bank to reach B as soon as possible? Assume there's no current in the river. Okay. So first we have to figure out what it is we're trying to optimize. So we're definitely not trying to optimize distance. Optimizing distance between 2 points is actually very easy. The shortest distance between any 2 points is a straight line. That's not what we're actually looking to optimize. She needs to get there as soon as possible, as fast as possible. We are looking to minimize time. Now we have all kinds of constraints, things like how wide is the river, how far downstream are we going, but notice a lot of our constraints contain things like speeds. Now in calculus, speeds are referred to as rates. We need to talk about distances, how far does she have to go? And when you start mixing things like, oh, I need to talk about times, rates, and distances, it really brings right back to mind that whole idea of, oh yeah, by the way, distance equals rate times time. Now we need an equation that talks about how long this is going to take, the time. So really what I want to do is solve this for time and think about the fact that time in general is a distance divided by a rate. Now that's true overall. And let's talk about what that means in the context of this problem. She's got some options. I mean, she can either row directly across the river and then run as fast as she can, so spend a lot of time on land. She can completely row all the way to point B, that's an option, or she can row to some other point. Now this point D is not necessarily where you see it depicted. It can be anywhere in between C and B, including at C or at B. So she can row to some other place on the other side of the river and then choose to walk or run some of that distance. So what we need is an equation to describe how long that's all going to take. So let me start off by calling it capital T, because I mean this to be a total amount of time. So in general, the total amount of time it's going to take her is however she spends in the boat, so time rowing, plus however long she spends running. I'm going to call it walking, just because I don't want 2 hours. So the time rowing versus the time walking, add those together, that tells you how long it's going to take her to get to point B. But because of the fact that time is distance divided by rate, that means what I'm looking at is a distance she spends rowing divided by the rate she spends rowing plus the distance she spends walking divided by the rate she spends walking. Now, the rates are given. She can row at a rate of 6 kilometers per hour. She can run at a rate of 8 kilometers per hour. So those denominators are given. I just need to do a little work to figure out the distances. So I've filled in the rates, the rate at which she's rowing, the rate at which she's walking. Let's talk about the distances. The distance she's going to spend rowing, it goes from A to D. Okay, it may be 3, that's a possibility. If she goes straight from A to C, that distance would be 3. Or if she goes straight from A to B, that distance would be 8. So that is somewhere in between there. But I need a way to represent it in general. So this distance here, take a look at the triangle I see forming here, here, and here. If I put a variable of, let's say, x on this leg right here, then notice it's a Pythagorean theorem that x squared plus 3 squared should equal that distance squared. So the distance will be the square root of x squared plus 9. The distance spent walking then goes from this point D, wherever it happened to be, this is the distance she's going to spend walking. So notice with the labels that I have on here, that distance is the total length of 8 with this x distance subtracted out. So it's going to be 8 minus x. So notice that by applying all these constraints, I already have t, the time, as a function of x. I don't have to apply any other constraints. It's already a function of one variable. So I'm just going to clean this up a little bit because I know I'm going to have to take a derivative. So it's 1/6 times x squared plus 9 to the 1/2. Plus, if you divide the 8 into both terms in the numerator, you get 1 minus 1/8 x. And that should help me out when I go to take my derivative. So I'm going to drop the 1/2 times 1/6 gets me 1/12. Here comes chain rule. That's x squared plus 9 now to the negative 1/2 times the derivative of the inside function, which is 2x. The derivative of 1 goes to 0, and then the derivative of the last term is negative 1/8. So we're going to take this and we're going to set it equal to 0. So in other words, the 2 and the 12, I'll be left with a 6 in a denominator. The square root goes to the bottom. That's x squared plus 9 under a square root in the denominator. That's 9. In the numerator, I will have an x. And then when I move the 1/8 to the other side, that's going to be equal to 1/8. So in other words, if you cross multiply, we're going to get 8x equals 6 square root x squared plus 9. In other words, you get 64. X squared equals 36 times x squared plus 9. Simplify, that will give you x equals 9 divided by the square root of 7. So that's my critical number. But again, as we saw in the last example, we need to check and see if letting x equal 9 square root 7 is in fact going to give me the fastest time or the smallest amount of time by plugging that into my time function. But I'm also going to have to take into consideration what would happen if she were to have rowed directly across and then run all the way down. And remember, this is what I have represented as x. Well, if she rows all the way across, this d is the same thing as c. Well, in that case, x is 0. The other possibility was that she rowed all the way to point B, in which case this d would be all the way down here, and in that case, x would be the entire distance. It would be 8. So I need to check all 3 of these and see what kind of time I'm going to get. If you plug in 9 divided by the square root of 7, you end up with 1 plus the square root of 7 divided by 8. That's about 1.33, and we are measuring our time in hours. If you plug in 0, you actually end up with this term zeroing out, and you get 3 here. 1/2 when you divide it by 6 plus 1 gives me 1.5 hours. And when you plug in 8, you end up with the square root of 73 over 6, which is about 1.42 hours. So notice the smallest of all of those does in fact occur at my critical number. So in other words, she needs to land 9 divided by the square root of 7, which if you want a decimal approximation for that, that's about 3.4 kilometers downstream if she wants to get there in the fastest time possible.